Hey guys, Ms. Gosling here. In this video, you're going to learn about the Bohr model of the atom. By the end of the video, you will be able to describe and solve problems involving the Bohr model of the atom. So let's go ahead and get started. So the Bohr model of the atom is a very simple model of the atom. And this is the model that you are probably used to talking about in your chemistry classes. So the Bohr model of the atom has a positively charged nucleus surrounded by different energy levels with electrons orbiting around it. So again, we have a positively charged nucleus and electrons orbiting that nucleus at different energy levels. The lowest energy levels being closest to the nucleus and the higher energy levels being farther away. Now, the Bohr model makes a few assumptions. First, under the Bohr model, we assume that electrons exist in stationary states, which we call often our energy levels. We also assume that electrons may move from one stationary state to another by absorbing or emitting a photon. So what that means is if we have two energy levels in our atom, like so, energy level 1 and energy level 2, and my electron wants to go from level 1 to level 2, what it's going to need to do is absorb a photon, which we're going to represent by that squiggly line, and that photon must have an energy equal to Planck's constant times the frequency of the photon. And just a note, h is equal to 6.626 times 10 to the negative 34th. So the electron at my first energy level is going to absorb a photon of energy h times the frequency of the photon, or h times the speed of light, divided by the wavelength of the photon, and that will allow it to jump to the next energy level. And then finally, we are going to represent the angular momentum by mass times velocity times radius is equal to nh over 2 pi. The angular momentum of an electron is represented by mass times velocity times radius is equal to n, which is the energy level number, times Planck's constant divided by 2 pi. So these are your two key equations for this topic. So when we apply the Bohr model to the hydrogen atom, which has, as you know, one proton and one electron, what we get is that the energy at any given energy level is equal to negative 13.6. So again, E is energy at a given orbital is given by negative 13.6 times the orbital number squared. And just so you're aware, negative 13.6 is the energy at the ground state. So at the lowest possible energy level, n equals 1. So this is going to be our key equation for understanding the energy transitions in a hydrogen atom. However, before we can use this equation to solve problems, there's one thing you need to know. The energy here is given in electron volts, not joules. So if you want to use any of our equations involving H, so for example, delta E is equal to H times F, or delta E is equal to HC over lambda, you're going to need to convert from electron volts to joules using our conversion factor of 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So just a reminder to everybody that that is a really important thing to do in these problems. So with all of that, let's go ahead and start with one example problem. How much energy is required to go from the first atomic energy level to the third atomic energy level? And for this problem, we're going to assume in a hydrogen atom. So what we want is delta E, which is going to equal the energy at our third state divided by the energy at our first atomic, or at our first orbital, our first energy level. So that's going to be negative 13.6 over 3 squared minus negative 13.6 over 1 squared, giving me that the change in energy is approximately 12.1 electron volts. Now I can of course convert this into joules by multiplying by 1.6 times 10 to the negative 19th to convert into joules. I'm not going to do that with the math there, but you guys can all see how that would happen. And there you have it. That is how I can calculate the energy required to go from one atomic energy level to another atomic energy level in a hydrogen atom. Now, one thing I would like to note, if we are looking at going from a higher energy state to a lower energy state, so for example, from our third energy level to our first energy level versus the other way around, rather than absorbing energy, we're going to actually release energy. So just a note there. If you got a negative answer here, that would mean that that energy was released instead of absorbed. Let's look at another example. So an electron drops from the fourth energy level to the third energy level, releasing a photon. In what part of the EM spectrum would you expect to find that photon? So we want to figure out the approximate wavelength or frequency of the photon in order to figure out where in the electromagnetic spectrum that might be. So our givens here is that we are starting at the fourth energy level and we're ending at the third energy level. We know that energy at the first energy level is negative 13.6, and we know that H is equal to 6.626 times 10 to the negative 34th. So with that, we're ready for our unknown. And I'm going to go ahead and say that my unknown is frequency, just because that's a little bit of a prettier equation, and we can use either lambda or frequency. So of course it makes sense to do the easier one here. So our equation here is going to be delta E, is equal to H times F, so Planck's constant times our frequency. And you'll note that I need to convert delta E into joules rather than leaving it in electron volts. So I'm also going to need to use delta E is equal to negative 13.6 over my final position squared minus negative 13.6 over my initial energy level squared, times, of course, 1.6 times 10 to the negative 19th to go from electron volts to joules. Thus, H times my frequency, or even more nicely, my frequency, is equal to negative 13.6 over my final energy level squared minus or plus 13.6 over my initial energy level squared times 1.6 times 10 to the negative 19th. All of that divided by Planck's constant. So now I am ready for my final step, which is to sub and solve. So plugging in my numbers, what I get is that my frequency is equal to negative 13.6 over 3 squared plus 13.6 over 4 squared. All of that multiplied by 1.6 times 10 to the negative 19th and divided by 6.626 times 10 to the negative 34th. And when I get that my frequency is equal to negative 1.6 times 10 to the 14th hertz. So now all I have to do is take this value for my frequency and figure out what part of the electromagnetic spectrum that puts me on. Looking at my electromagnetic spectrum, I see that 10 to the 14th hertz, right here, puts me nicely in the spectrum of visible light. So there you have it. There is my answer. My frequency the frequency of the emitted photon is going to be in the visible spectrum. So let's go ahead and talk takeaways. First of all, the Bohr model is a widely accepted model of the atom. Now I will note, it's actually inaccurate. I know, that's annoying. It doesn't take into account quantum mechanics, so it's not fully correct, but it's a really useful model for solving a lot of problems like this one. And so for understanding things like absorption and emission spectra, which we'll get into in the next video, the Bohr model is a really helpful way to do that. Again, it is not actually accepted as being correct, but it is accepted as being correct enough to be useful in most situations. So our second takeaway, in the Bohr model, electrons exist at specific energy levels, which we call stationary states. And finally, electrons can travel from one energy level to another by absorbing or emitting photons. So there you have it, folks. That is the Bohr model of the atom. Go ahead, watch the next video on absorption and emission spectra, and see if you can solve some of these problems on your own. Best of luck, and happy solving!